Hello everybody, my name is Monira Mahmoudi. I am a PhD student in the field of transportation engineering in the School of Sustainable Engineering and the Built Environment at Arizona State University. This presentation is the joint work of my advisor, Dr. Susang Jo, and I on the ride-sharing problem. In this presentation, we initially start with motivations of this research. We introduce the ride-sharing problem and the corresponding literature. Since the ride-sharing problem can be mathematically modeled by one of the well-known optimization problems, which is vehicle routing problem with pickup and delivery with time windows, we will briefly explain this important optimization problem, and then we will describe the theoretical and computational challenges for solving this specific problem. After that, we comprehensively explain our proposed network representation and mathematical model, and then we go through the details of our solution approach, which is a combination of time-dependent forward dynamic programming and Lagrangian relaxation method. Finally, we will show our results and finish our presentation with a short conclusion and future trend of this research. You all definitely know that having a car is really costly, while public transportation is still not that much efficient. Every day we waste a huge amount of time due to the traffic congestion. In fact, traffic congestion has brought several unavoidable problems for human beings, such as air and water pollution. In the field of transportation engineering, several solutions have been offered to reduce the negative effects of traffic congestion. Ride-sharing is one of these resolutions. In a city with numerous travelers with different trip purposes, each traveler has his own traveling schedule. Instead of using his own car, the traveler can call a car just a few minutes before leaving his origin or pre-schedule a car a day prior to his departure. The on-demand transportation system provides a traveler with a short waiting time even if he resides in a high-demand area. Currently, several real-time ride-sharing, or more precisely, app-based transportation network and taxi companies such as Uber and Lyft are serving passengers in many metropolitan areas. Actually, the ride-sharing problem is mathematically modeled by one of the well-known optimization problems, which is vehicle routing problem with pickup and delivery with time windows. To briefly explain this optimization problem, let's assume that we have a single depot with 3 vehicles available in it. Each passenger has a specific origin and destination. In addition, each passenger wants to be picked up in a specific time window and be dropped off in a particular time window. What we need to find in this problem is that, first of all, we are going to find the best possible routing and scheduling of our vehicles. Second of all, we would like to find the optimal assignment of passengers to our vehicles. And finally, we would like to find the optimal price that we can offer as a service provider company to each passenger so that we do not lose any profitable passenger. Several researches have been done for solving this challenging optimization problem, and several solution approaches have been proposed, such as Bender's decomposition, branch and bound, branch and cut, branch and bound and price, column generation, dynamic programming, set partitioning, and etc. However, this problem, even for a small number of passengers and vehicles, is still very hard and challenging. To show the difficulty of this problem, let's look at this example. Let's assume that we have a 6-node transportation network. We have 2 passengers with the same origin, which is node 2, and the same destination, which is node 3. Assume we have 2 vehicles available at the origin depot, which is node 4, ready to serve these 2 passengers. Assume that these 2 vehicles, after finishing their task, should come back to the ending depot, which is node 1. As we discussed before, each passenger has a preferred departure and arrival time windows. For example, here, the first passenger wants to be picked up between time 4 to 7 and drop off between time 9 to 12, while the second passenger departure time window from his origin is 10 to 12 and his arrival time window to his destination is 15 to 17. As you may have already noticed, these two passengers, due to their preferred time windows, cannot share their ride with each other. Therefore, each passenger should be assigned to a vehicle individually. In this slide, we show how vehicles dispatch from the depot to serve these two passengers. In this example, the first vehicle starts its route from its origin at time 4, then go to node 2 to pick up the first passenger, and after picking up passenger 1, the vehicle chooses the shortest path to deliver the passenger to its destination. Finally, the vehicle ends its route to its ending destination. As you can see, when vehicle 1 was involved in serving passenger 1, vehicle 2 dispatched to serve the second passenger. In fact, the existing network representation does not work with the transportation networks directly. Instead, it includes passengers and vehicles' origin and destination. The links between the nodes are the shortest path between each node to other nodes of the network. This is the current mathematical formulation for the vehicle routing problem with pickup and delivery with time windows. In addition, the mathematical formulation corresponding the existing network representation contains two groups of nonlinear constraints, one for time windows constraints and the other one for vehicles capacity constraints. Now it's time to ask this question that, what if instead of having a 6-node transportation network, we have a real transportation network with thousands of nodes and links? What if we have thousands of passengers, tens of depots, and hundreds of vehicles? Then, if we would like to route and schedule our vehicles in an online network, can we still use the existing network representation? With this introduction, we are ready to start our discussion about our proposed network representation and mathematical model. As we mentioned before, in this research, we work with the transportation networks directly. The numbers written on each link is the travel time. First of all, to distinguish physical transportation nodes from origin and destination of vehicles and passengers, we add a dummy node corresponding each passenger and each vehicle's origin and destination. Then, we connect these dummy nodes to the corresponding physical transportation node by a link whose travel time can be interpreted as the service or preparation time. Then, we extend our physical transportation network over the time to be able to find the time-dependent shortest path between nodes easily. Our network representation is still incomplete. We need to add another dimension. This new dimension is the passengers carrying state dimension. Let's describe this dimension by an example. In the left-hand side figure, our vehicle starts from the depot, then goes to the origin of passenger 1 to pick up the first passenger, and then goes to passenger 2's origin and pick up the second passenger. Now our vehicle carries both passengers. This is exactly the meaning of the passengers carrying state. Let's look at another example. In the right-hand side, the vehicle starts its route to pick up the second passenger. As you can see, the state corresponding the link O2D2 contains only passenger 2. It means that the vehicle is carrying passenger 2 right now. The table above shows all possible combinations of passenger carrying states in which the vehicle can only serve up to 2 passengers. As you can see, the pickup action only occurs when a single passenger is added to the state, and similarly, the drop-off action occurs when a single passenger is eliminated from the passenger carrying state. The graph below shows these combinations better. The green links are representative of pickup action and blue ones are representative of drop-off actions. Now it's time for us to extend our space-time network over the state dimension. In this example, we have two passengers with different origins and destinations. One of them wants to go to his office and the other one wants to go shopping. We initially map the two-dimensional space to one-dimensional space, and then we add a new dimension, which is passengers carrying state, to our network. By having this three-dimensional network representation, we are able to mathematically model the vehicle routing problem with pickup and delivery with time windows. This figure is the projection of three-dimensional state, space, time network on two-dimensional state, space network. As you can see, the vehicle starts its route from the empty state in which it does not carry any passengers, then goes to the origin of first passenger to pick him up. Now the vehicle carries passenger 1. Therefore, the passenger's carrying state changes from empty state to P1. Now it's time to pick up the second passenger. Again, the passenger's carrying state is changed from P1 to P1, P2. It means that the vehicle is carrying both passengers right now. Then, the vehicle chooses the shortest path to deliver the passengers. The vehicle drops off the first passenger and the state is changed to P2. Then, it is time for second passenger to be dropped off. Again, the passenger's carrying state is changed from P2 to the empty state. At the end, the vehicle comes back to its depot with the empty state. As you may have noticed, by our well-structured network, we can pre-build the vehicle capacity constraints, time windows constraints, and the precedence constraints. Okay, now it's time for us to mathematically model this time-discretized multi-commodity network flow optimization problem. First of all, in this research, we are going to minimize the total travel cost. Please note that the routing cost of a transportation arc is defined as a ratio of its travel time. Then, we write the flow balance constraints for the origin and destination of each vehicle and also for any intermediate node of our network. We also need to add a constraint to guarantee that each passenger is picked up exactly once by one vehicle. Moreover, we need to have a constraint to ensure that each passenger is dropped off by the same vehicle which has been picked up the passenger already exactly once. And finally, we should ensure that all variables are integer. Note that each vehicle must end its route at the destination depot with the empty passenger carrying state. Therefore, if vehicle V picks up passenger P from his origin, to maintain the flow balance constraints, the vehicle must drop off the passenger at his destination node so that the vehicle comes back to its ending depot with the empty passenger carrying state. As a result, constraints corresponding to the passenger's drop-off request is redundant and it does not need to be inserted into the following formulation. In this slide, we will relax the constraints corresponding passengers picking up to convert the problem to a time-dependent least cost path problem. Several efficient algorithms have been proposed to compute time-dependent shortest paths in a network with time-dependent arc costs. In this research, we use a time-dependent dynamic programming algorithm to solve the least cost path problem. This slide presents the time-dependent forward dynamic programming that we have used to solve the problem. Interested readers can find more details about Lagrangian relaxation solution approach and time-dependent forward dynamic programming in our paper, which has been published recently in the Journal of Transportation Research Part B. We tested our algorithms on the 6-node transportation network by 6 different scenarios in which different number of passengers and vehicles are in the system. Our results show that our algorithm is stable and no passenger is remained unserved. In this table, as you can see, by increasing the number of passengers and vehicles, we have a very small gap between lower bound and upper bound of our objective function, which is less than 5%. One of the beauties of this solution approach is finding this graph. As you can see, after some iterations, the value of Lagrangian multipliers are converging to a specific value. This value can be interpreted as the optimal price that the service provider can offer to each passenger. We also tested our algorithm on the median scale transportation network, which is Chicago sketch network with around 1,000 nodes and 3,000 links, and as you can see, by increasing the number of passengers and vehicles, the results are still stable. We also tested our algorithm on the large-scale transportation network, which is Phoenix network with around 14,000 nodes and 34,000 links. As results shows, the gap between lower bound and upper bound is less than 5%, which is acceptable. To this end, in this research, we proposed a new mathematical formulation for the ride-sharing problem, the very important problem in the field of transportation. By using three-dimensional state, space-time network representation and the Lagrangian relaxation solution approach, the main problem is simplified to a time-dependent shortest path problem, which can be solved by efficient algorithms without too much computational effort. In addition, unlike former proposed models, our network is able to solve the pickup and delivery problem directly on the real-world transportation networks. In the future, we may also extend our research in order to handle some special cases of pickup and delivery problem. For example, there might be some passengers who desire different ride-sharing capacities. It means that one passenger may desire to share his ride up to only one passenger and the other passenger does not care about the number of passengers present in the vehicle. The other special case is that some passengers would like to be served by a specific type of vehicles or specific drivers. And finally, we would like to simplify our network representation for those transportation requests that have the same origin but different destinations or different origins but the same destination. Thank you very much for watching this video, and I would be more than happy to find your comments and ideas about our research.